energetic entities in the universe are. Today we delve into the fascinating world of quasars, the celestial powerhouses that outshine entire galaxies. The story of quasars begins in the 1950s, when astronomers detected mysterious sources of radio waves. These were initially dubbed quasi-stellar radio sources, which was eventually shortened to the term we use today, quasars. At first, when viewed through telescopes, these sources appeared as faint points of light, resembling stars. Hence the name quasi-stellar, meaning star-like. However, as technology advanced and our understanding deepened, we realized that these were no ordinary stars. Quasars, it turns out, are formed by supermassive black holes, each with a mass ranging from millions to billions of times that of our Sun. These black holes are surrounded by a disk of accreting gas, which is accelerated to incredible velocities and temperatures through gravitational interaction with the black hole. This process releases a monstrous amount of energy in the form of electromagnetic waves, including radio waves and visible light, making quasars the most powerful energy emitters in the universe. A single quasar can outshine a galaxy like our Milky Way by thousands of times. One of the most intriguing aspects of quasars is their redshift. Light emitted by quasars shows a high degree of redshift, which is a cosmological effect indicating the great distances between us and these quasars. This discovery led astronomers to the realization that quasars are far-flung objects from a much earlier stage in the universe's history. In fact, astronomical surveys reveal that quasars were more common in the distant past of our universe, peaking about 10 billion years ago. The most distant quasar known to us as of December 2017 is ULAS J 1342 plus 0928, with a redshift of 7.54. The light we see from this quasar was emitted when the universe was a mere 690 million years old, and the black hole at its core has a mass estimated at 800 million solar masses. Quasars are not just fascinating for their distance or their power. They are also among the most luminous, energetic objects in the universe, residing at the centers of young, active galaxies. They emit energy at a rate that can exceed the brightness of an average galaxy, equivalent to 2 trillion suns. This radiation is emitted across the electromagnetic spectrum, from X-rays to infrared, with a peak in the ultraviolet and optical bands. Some quasars are also powerful sources of radio and gamma-ray emissions. In summary, quasars are celestial powerhouses formed by supermassive black holes. They are the universe's most powerful energy emitters, capable of outshining entire galaxies. The light they emit shows a high degree of redshift, indicating their great distances from us and their origins in the early universe. They are most common in young, active galaxies and were more prevalent about 10 billion years ago. Quasars truly are the most fascinating objects in our universe, serving as windows to its distant past and giving us insight into the cosmic forces at play.
Have you ever contemplated how the intense rivalry of the Cold War ignited a spectacular competition that shot humanity beyond the confines of our atmosphere? This is the story of the space race, a thrilling chapter of history where the United States and the Soviet Union turned their sights to the stars, transforming the realm of science fiction into tangible reality. In the wake of the Second World War, as the dust of conflict settled, a new form of rivalry emerged. Two superpowers, the United States and the Soviet Union, were locked in a political and ideological confrontation known as the Cold War. Amid this tense standoff, the space race became a pivotal battlefield, a competition not just of military might but of technological prowess and national pride. The genesis of the space race can be traced back to the late 40s and early 50s, when both nations began developing ballistic missiles, the precursors to the rockets that would later propel astronauts into space. The space race officially ignited on October 4, 1957, when the Soviet Union launched Sputnik, the first artificial satellite, into space. This event sent shockwaves around the world, demonstrating the Soviet Union's advanced technological capabilities. The United States responded to this provocation by intensifying its own space program. In 1961, President John F. Kennedy famously declared the nation's bold goal to land a man on the moon before the end of the decade. This proclamation marked a turning point in the space race, shifting the focus from merely reaching space to exploring beyond our planet. The following years were marked by a series of pioneering missions. Robotic probes ventured to the Moon, Venus, and Mars, opening up these celestial bodies to human understanding. astronauts and cosmonauts orbited the Earth, breaking free from the bonds of gravity and entering the realm of the cosmos. The climax of the space race came in the summer of 1969 when the United States achieved its ambitious goal. On July 20th, the world held its breath as Apollo 11 landed on the moon, and Neil Armstrong took his historic first step on the lunar surface. The space race had reached its zenith, but the exploration of space continues to this day. To summarize, the space race was a unique chapter in human history, a period when two rival nations turned their conflicts skyward. It began with the development of ballistic missiles in the post-World War II era, and officially ignited with the launch of Sputnik in 1957. The competition escalated with President Kennedy's moon landing challenge in 1961 and culminated with the successful Apollo 11 mission in 1969. The legacy of the space race is still alive today, as humanity continues to reach for the stars, driven by an insatiable curiosity and a desire to push the boundaries of what is possible.
Have you ever wondered about the astronomical costs involved in sending payloads into low Earth orbit? What if there was a more cost-effective and efficient solution than traditional rocket launches? The answer might lie in a concept called a skyhook. A skyhook is a proposed momentum exchange tether system designed to reduce the cost of placing payloads in low Earth orbit. Picture this: a heavy orbital station is linked to a cable which extends towards the high atmosphere. This is the skyhook. Now let's imagine we have a payload that we need to launch into orbit. This payload is much lighter than the orbital station. The payload is hooked onto the end of the cable as it passes by, and then launched into orbit by the rotation of the cable around the center of mass. After the payload is launched, the orbital station can be reset to its original altitude. This can be achieved by using electromagnetic propulsion, rocket propulsion, or by deorbiting another object with the same kinetic energy transferred to the payload. A skyhook differs from a geostationary orbit space elevator because it would be much shorter and wouldn't make contact with the Earth's surface. It would require a suborbital launch vehicle to reach its lower end, whereas a space elevator wouldn't. In this video, we've delved into the concept of a skyhook, a tether system that could potentially cut down the costs of launching payloads into low Earth orbit. We've looked into how it works, how it is connected to an orbital station, and how payloads are launched into orbit. We've also explored the benefits of a skyhook, such as its potential to be more cost-effective and efficient than traditional rocket launches. As we push forward into the future of space exploration, concepts like the skyhook could pave the way for more accessible and affordable journeys into the cosmos. The skyhook is just one of the many innovative ideas that could change the way we venture into space. It's an exciting time to be a space enthusiast, as the possibilities for what we can achieve are as limitless as the universe itself.
Ever pondered the dawn of existence? It all began with pure energy, and then the strings vibrated. Welcome to the exploration of string theory. String theory puts forth a rather intriguing proposition that the universe, in its intricate complexity, is composed not of point-like particles, but of minuscule, vibrating strings. Picture the world we live in. It exists in 3 spatial dimensions and 1 temporal dimension, right? However, string theory dares to push the boundaries of this understanding. It suggests the existence of additional dimensions, as many as 10. Each string is unique, vibrating at its own distinct frequency. This vibration, as it turns out, is the key to determining the mass and charge of the particle represented by the string. The beauty of string theory lies in its potential to bridge the gap between 2 fundamental pillars of physics, quantum physics and general relativity. It has the potential to unify these 2 seemingly disparate realms, offering a coherent picture of the universe. However, despite its elegance, string theory isn't without its fair share of criticism. Is it truly the theory of everything, or is it merely a beautiful mathematical construct with no grounding in reality? Regardless of the challenges faced, the pursuit of knowledge remains relentless. And who knows, perhaps we are just one vibration away from unraveling the secrets of the universe. End. Have you ever gazed up at the night sky and wondered if we are truly alone in the universe? What if, scattered across the cosmos, there are planets teeming with life forms unimaginable to us? This is not just the stuff of science fiction, it's the very real, thrilling pursuit of astrobiology. Astrobiology, often known as exobiology or bioastronomy, probes the profound questions about the origins, evolution, distribution, and future of life, both on Earth and potentially elsewhere in the universe. It's a detective story spanning galaxies and epochs, where each clue unravels part of the grand tapestry of life. At its core, astrobiology relies on an interdisciplinary approach. Chemistry provides the building blocks of life, revealing how simple molecules in space can form complex organic compounds. Biology then takes these compounds and explores how they could assemble into living organisms, adapt, and evolve in diverse environments. Astronomy offers a wider lens, pointing us to where these chemical and biological processes might occur beyond Earth. It guides us through the cosmos, identifying planets and moons that could harbor life. Geology helps us understand these extraterrestrial landscapes, studying planetary surfaces and atmospheres to predict where conditions might be ripe for life. Space technology is the tool that binds all these disciplines together. It enables us to send probes and telescopes into the far reaches of space, to collect data and observe planets and moons up close. Each mission, whether it orbits Mars or passes by a distant comet, contributes valuable information to our understanding of life's potential spread across the universe. Astrobiology also delves into the study of extremophiles, organisms that thrive in Earth's harshest environments. These hardy creatures offer clues about the resilience of life and the variety of conditions under which life can sustain itself. From boiling hydrothermal vents to the frozen wastes of Antarctica, life's tenacity continually surprises and enlightens us. The search for biosignatures or markers of life extends this research beyond our solar system. It involves meticulous analysis of atmospheric gases, surface compositions, and even the light from distant exoplanets to detect possible signs of biological activity. In conclusion, astrobiology isn't just about finding aliens. It's a comprehensive study that challenges our understanding of life itself. It merges multiple scientific disciplines to not only seek out where life could exist, but also to understand how life begins, survives, and impacts its environment. The pursuit of this knowledge excites the imagination and drives scientific innovation, reminding us of the boundless possibilities that await in the vastness of space.